Alrighty, so we've seen how to choose an estimator for a regression problem. How could we do the same for a classification problem? Well, first of all, let's get a data set that is a classification problem back in our MITs. So we want data. We've already imported this above, but we're just going to do it again just so we have it. CSV, just to make sure it's the same. Heart disease dot head. Wonderful. So again, we've seen this data set before. We want to use these columns of patient. Each row is a patient, so each sample is a patient. Each column or each feature is a health attribute of that particular patient. And the target, 1 or 0, is whether that patient has heart disease or not. So our model, classification, predicting something is one thing or another, heart disease or not, that's what we need. So what we're going to do is we left ourselves this little link here to go visit the map. So we're going to pay attention to that. We go here. So we know we want something in the classification realm. But what we're going to do is we're going to start from the top and follow this through. So start. Do we have above 50 samples? Well, let's check. Each row is a sample. So we want Len, heart disease. 303. Yes, we can. Are we predicting a category? Are we? Heart disease or not heart disease? Sounds like a category to me. Yes. Do we have labeled data? Yes. Do we have under 100k samples? Yes. What is this? We reach a little green box. Beautiful. So remember, the green boxes are estimators or machine learning algorithms. So let's have a look. This is telling us our problem's classification, and maybe the first one we come to is trying a linear SVC. Well, all right. Classification. SVC and linear SVC are classes capable of performing multi-class classification on a dataset. Well, this one particularly said linear SVC. So let's have a look. Linear support vector classification. Similar to SVC with parameter kernel linear, but implemented in terms of liblinear rather than libsvm. Whew, that's a lot of terms there, and most of them I don't really understand. But what's important here is that if we go down to the code example, we can see from Scikit-learn.svm import linear SVC xy. Oh, they've used x and y. CLF classifier equals linear SVC. All right, this is kind of similar. Well, let's not take the documentation's word for it. Let's try it for ourselves. We'll go import. Actually, we'll leave ourselves a note. Consulting the map, and it says to try linear SVC. So that'll be our first protocol. Import the linear SVC estimator class. I'm going to go from Scikit-learn.svm, and really what I'm doing here is I'm basically just going to rewrite this, but for our problem. So Scikit-learn.svm import linear SVC, import linear SVC, wonderful. Set up random seed, mp.random.seed, and we'll use our faithful 42, and then we're going to go make the data. We saw this in the previous section, section 1, get your data ready. X equals heart disease dot drop. We want to get rid of the target column on axis equals 1, and y equals heart disease. Y is actually the target column. Beautiful. And then we're going to go split the data. X test. Or no, train comes first. Silly me, I've done this about 100 times by now, and we're still getting it wrong. See, this is what it takes. It takes a little bit of practice, or it takes a lot of practice to start applying, start becoming a machine learning practitioner, knowing how to deal with data, knowing how to split data, knowing how to model data. It's all part of the practice. Test size, yes, that is correct. That's what we want to do. Instantiate linear SVC. So we'll call it CLF, short for classifier. Linear SVC. And we're going to go, that'll do actually, CLF.fit. We want X-train, Y-train. And then we're going to go evaluate the linear SVC. CLF.score X-test, Y-test. All right. Beautiful. Let's see this in action. Wonderful. Linear failed to converge. Increase the number of iterations. Well, this is one of those things where if you came into an error like this, what I might do is go convergence warning. I'd Google this message and see what came up. Because I've had a little bit of experience with it, I might do something like max iter equals 1,000. And it still happens, right? So increase the number of iterations. We've done that. We've gone max iter equals 1,000. But this is actually, how much does it start? Max iteration, it's default by 1,000. Let's see, 10,000, still there. Well, let's bypass that for the time being. We're getting a warning. And see here, the score is below 0.5. Now, why is that a trigger in our heads? Well, because if we look at our data, we want heart disease, target, dot, value counts. So we see there's only two classes, 1 or 0. Does someone have heart disease or not? Right, so it's a binary classification problem. Binary meaning one or the other. And our model is receiving a score of 0.47, returns the mean accuracy on a given test data and labels. As I said, we'll look into evaluation metrics in a future section. But what you can imagine this is our model is only operating at 47% accuracy. And why does that trigger us? Well, because there's only two classes. So that means if we were just guessing whether someone had heart disease or not, but based off their health attributes, we were just guessing yes or no, we would get 50%. It's basically a coin toss. So what's that triggering in our head? It's saying, hey, without fixing this warning or without improving our model by tuning the hyperparameters, our linear SVC model might not be finding patterns between X and Y. So what can we do? Well, when in doubt, come back to the graphic. Not working. Are we working with test data? Because we just tried linear SVC, so we're going to say not working. Are we working with test data? No. Well, this is going to say k-nearest neighbors classifier, but I'm going to skip this one. I'm going to go to ensemble classifiers. So let's click on this. Now, why this? Because we've seen this before. Ensemble methods, forest of randomized trees, Scikit-learn ensemble. From Scikit-learn ensemble, import random forest classifier. Now, if you remember, back up in our regression problem, when we switched to using a random forest regressor, we saw a bump in the score. Well, because random forest regressor did so well, good news is for us, it's got a dance partner called random forest classifier. We've actually seen this before, but what we're going to do is compare it to linear SVC. So to save time, I'm going to copy this code and I'm going to bring it down here. So we want to change this to random forest classifier. We actually want ensemble, import random forest classifier. Wonderful. We can keep the rest the same except for this. We need to actually sub this out. Random forest classifier. And we want to go random forest classifier. Wonderful. We'll do the same here just to tidy up our notes, keep our code communicative. Wonderful. And now what do you think will happen here? 3, 2, 1. Let's see. Error. Fit. Missing one argument. Why? Oh, there we go. That's what we forgot. We forgot to add the little brackets on the end. Wonderful. Now to get rid of this warning, we need to change n estimators, because see here, the default value of n estimators will change from 10 in version 0.2 to 100. So we'll just get rid of that by changing n estimators equals 100. Delicious. Wonderful. So what's happened here? We've used a different model. Now, linear SVC has scored 47% accuracy, and our random forest classifier has scored 85% accuracy. So nearly double by just using another model. Right, so you can see why I'm kind of jumping to using random forest. If we go back, all I've done is I've gone start. I figured out what kind of problem we're trying to solve. You can do this as well. So for our regression problem, we were trying to figure out whether something was a number. For our classification problem, we were trying to predict the label. Do we have labeled data? Yes. Are we predicting category? Yes. And now our linear SVC model wasn't working, so we went straight to ensemble classifiers. And now you might be thinking, What about all the other models, right? So we've kind of skipped all these ones here. All of these, and we've only really touched the surface. We've only used this one and ensemble classifiers for both. And that's a great question. Well, the first reason is, namely for time. We could go through and try all of these. And the second reason is, there's a little tidbit in machine learning. If you have structured data, aka tables or data frames, use ensemble methods, such as random forest. Why? Because it'll perform pretty well. If there are patterns, this is a tidbit here, heart disease. Might write this down so we know. I'll put this in a resources section as well. Tidbit is 1. If you have structured data, use ensemble methods. And 2 is if you have unstructured data, use deep learning or transfer learning. Now, what's an example of structured data? Well, stuff in a table like this. And if we have unstructured data, which is like images, audio, or text or something like that, use deep learning or transfer learning. Now, we haven't covered deep learning or transfer learning yet, but since we have structured data, aka things in a data frame, the tidbit there is use ensemble methods, which is hence why we've kind of gone, you know what, I'm not going to try any of these. I'm going to straight to ensemble classifiers, straight to the random forest, because the random forest is known for its robustness and ability to find patterns. Now, we've covered a lot. We've had a look at this machine learning map. If you're still looking at this going, holy gosh, what's going on? Don't worry, it took me a while to figure it out too. But it really clicked once I realized, hold on, the first step is to just get the data, figure out the main problem we're trying to solve. Usually regression or classification, they're the two most common ones you'll come across. And then start answering the questions going through it, and then use a little framework, something as simple as this, to start running a machine learning estimator or machine learning model on your data and getting some feedback from it quickly. That's the most important part. Being a data scientist or machine learning engineer is reducing the time between your experiments. So what we're going to do now is we've seen how to choose a model. We're going to get into the next section, which is fitting a model to the data and then using it to make predictions, because that's really the essence of machine learning, right? Finding patterns in data and then using those patterns to make predictions on future data a model hasn't seen before. Take a quick break and I'll see you in the next video.